Welcome. Today, we are diving headfirst into a physics puzzle that honestly feels like it shouldn't be possible. We're going to tackle a classic problem that trips up a ton of students. And I promise, by the end of this, you'll see exactly how a piece of something can end up moving way faster than the original object ever was. So, here's the paradox that messes with your brain. You've got a shell. It's flying along at 500 meters per second. Then, boom, it explodes. Now, your intuition probably tells you the fragments are going to fly off, sure, but they should all be moving slower than the original shell, right? It just makes sense. So how on earth is it possible for one of those fragments to suddenly be zipping along at twice the speed of the whole thing?
Now, this isn't just some random thought experiment. This is a legendary problem from the Irodov physics textbook. Let's get specific. The shell is moving at 500 meters per second. It breaks into 3 identical fragments. And here's the giant clue. The total kinetic energy of the system actually increases by 1.5 times. Our mission, should we choose to accept it, is to figure out the absolute top speed one of those fragments can possibly hit.
And we're not going in blind. We've got a solid game plan. First, we'll open up our physics toolbox and grab the exact concepts we need. Then, we'll actually set up the problem and solve for that maximum velocity. After we get that aha moment with the answer, we'll figure out where all that extra speed came from. And to wrap it all up, I'll give you a simple framework you can use to solve any problem just like this one. Okay, first things first, let's get our toolbox ready. Before we even think about plugging in numbers, we have to be absolutely crystal clear on the 2 fundamental laws that are running this whole show. Getting these right is, well, it's everything. All right, tool number 1, the law of conservation of momentum. This one is non-negotiable for any isolated system, and an exploding shell is a perfect example. The total momentum you have before an event has to equal the total momentum you have after. An explosion is all internal forces. There's no outside rocket pushing on it, so the total momentum of our system is absolutely conserved. Now for our second tool, kinetic energy. You know, the energy of motion. And listen up, because this is the #1 trap students fall into. In an explosion, kinetic energy is absolutely not conserved. Think about it. An explosion releases energy, right? That chemical potential energy that was just sitting there in the gunpowder suddenly turns into the kinetic energy of all those flying pieces. It's a conversion, not a conservation. So let's put these two side by side, because this is where the magic happens. Momentum is a vector. Direction is everything. Kinetic energy is a scalar. It's just an amount. It doesn't care which way things are going. So in our explosion, momentum is conserved, period. No external forces. But kinetic energy? It actually goes up because that chemical bomb goes off. Understanding this single difference is honestly half the battle. All right, our toolbox is open, we know momentum is conserved, and we know kinetic energy is not just conserved, it actually increases. With those 2 big ideas locked in, let's walk through the solution step by step. Let's just lay out our variables so we're all on the same page. Before it goes boom, we have one object, let's call its mass big M, moving at velocity v. Simple enough. Its momentum is m times v, and its kinetic energy is 1/2 mv squared. After the explosion, we've got 3 identical pieces, so each one has a mass of big M over 3. They shoot off with new velocities, and the problem specifically tells us their total final kinetic energy is 1.5 times what we started with.
Okay, stop for a second. Let's put our physicist hat on. The problem doesn't just ask for a velocity, it asks for the maximum possible velocity. That's a huge hint. It means we're looking for a very specific, perfect scenario. So if you want to give one fragment the biggest possible kick forward, what is the absolute most efficient thing the other 2 pieces could do?
And that's the key insight right there. To launch one fragment forward as fast as humanly possible, the other 2 have to team up and recoil backwards as a single unit. It's just like firing a cannon, right? To get the cannonball flying forward at max speed, the heavy cannon itself has to recoil straight backward. Any momentum that goes sideways is just wasted. It's the exact same principle. So, that insight lets us build our equations. For momentum conservation, we can say the initial momentum equals the momentum of our forward piece plus the momentum of the 2 backward pieces. Then, from the energy rule, we know the final kinetic energy is 1.5 times the initial. And just like that, we have 2 equations and 2 unknown velocities. We have everything we need to solve for the maximum speed of that one fragment. So we've set up all the physics, we've figured out the most efficient way for this shell to explode. Now for the fun part. After you crunch the numbers, what do you actually get? What is the fastest that one piece can possibly be going?
1,000.
Meters per second. That's it. That's the answer. The shell was moving at 500 meters per second, and one of its own fragments ends up flying at double that speed. How cool is that?
And looking at it like this really drives it home. The initial 500 meters per second is just completely dwarfed by the fragment's maximum possible speed. This isn't some kind of trick question. It's a beautiful demonstration of how energy conversion actually works.
So let's answer our initial question. Where did that extra 500 meters per second of speed come from? It came from the explosion. That chemical energy that was neatly packed inside the explosive got turned into raw kinetic energy, giving that one lucky fragment a massive boost forward. And it was all paid for by kicking the other two fragments backward. And just like that, the paradox is solved.
You know, the real goal here wasn't just to solve one problem. It was to learn a method, a way of thinking. So let's boil down everything we just did into a simple, reusable framework that you can apply to pretty much any collision or explosion problem you come across.
Here it is, your 4-step guide. Step 1, always define your system, what it looks like before and after. Step 2, apply conservation of momentum. Seriously, this is almost always where you start. Step 3, analyze the energy. Ask that crucial question, is kinetic energy conserved or does it change? And finally, step 4. If a problem asks for a maximum or a minimum, you have to think strategically. Figure out the most efficient way things could happen, just like we did with the recoil.
And that pretty much brings us to the end. But I want to leave you with a challenge, a way to test out this new framework. What if the explosion was way more powerful? What if it tripled the kinetic energy instead of just increasing it by a bit? Could a fragment go even faster? How fast? Give it a shot, run it through the steps, and you'll find the physics works exactly the same. Only now you have the tools to solve it.